So welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So for tuning into OneClass for the first time, again, what we're doing here is at OneClass, what we're doing is we're providing some online resources such as live streams and videos for you to kind of tune in. So basically what we're doing here at OneClass is we're going through a session of just kind of verifying solutions asked by frequently asked questions asked by students. So this ranges from basically the secondary level in terms of chemistry and mathematics subjects, and it also it goes all the way to the university and college level in terms of chemistry and also math as well. So today what we're going to do is I'm going to kind of go over some frequently asked chemistry questions, and this is a pretty big range between basically grade 10 all the way up to kind of university or in organic chemistry as well. So I'm going to answer basically 10 questions about, or 10 to 11 questions about those types of topics. And that's going to be our hour for today. So my name is Joey. I'm currently an Ontario secondary school educator. My teachable subjects are indeed chemistry and mathematics. So hopefully I'll be able to kind of walk through the solutions with you, teach you the concepts behind the questions, and kind of explain my thinking as we go forth to do these questions as well. So without further ado, let's get started on today's problems for chemistry today. So what we have here is the first question is asking us, what is the formula for hydrosulfuric acid? So this is a pretty easy question here. It's kind of zoomed in again. I might have to refresh here. Okay. So I want the formula for hydrosulfuric acid. So what is the formula for hydrosulfuric acid? So I think I want to think about this question. We're going to start off pretty easy, and then we'll move on to much harder problems as we go forth. But it's asking us, what is the formula for hydrosulfuric acid? And there's actually a little error in terms of this question. There's no actually such thing as hydrosulfuric acid here. This compound doesn't really exist in terms of the IUPAC naming here. I think what the student was trying to ask here is, what is the formula for simply just sulfuric acid? Hydrosulfuric acid doesn't really make sense, just because this here is an oxyacid. You basically only use hydro when you have a binary acid here. So a sulfuric acid, example of an oxyacid. And you basically only use the prefix hydro if it's a binary acid, which sulfuric acid is not. So hydro reserved for binary acids. And if you want to know the difference between the oxyacids and what a binary acid is, binary acid, you could think of this as like HCl, something that's only made up of two compounds, a hydrogen and usually a halogen as well. So HCl, obviously, we know it's hydrochloric acid. And let me just write the aqueous state as well here. This here is, again, I know that this is hydrochloric acid. And an example of oxyacid here would be something with an oxygen. So for example, phosphoric acid, H3PO4. This here would be an oxyacid because it has an oxygen in it, right? Phosphoric acid. So it's asking us, what is the formula for so we know that this hydro is gone, right? So what is the formula for sulfuric acid? So in order for us to solve this question, we have to look at sulfuric acid here. Sulfuric acid comes from the polyatomic sulfate, right? So if I work backwards here, so sulfuric acid comes from the prefix of sulfate here, which is a polyatomic ion, right? Sulfate here, and if you remember from our rules here, ic acid is we're changing ic to 8, right? If we want to convert it back to a polyatomic, ic to 8 and us to ite here. So this is sulfate, and we know that sulfate here is SO4, right? Sulfate here is our polyatomic ion, very, very common, and this guy here is SO4 2 minus, right? So this here is our polyatomic ion. SO4 2 minus. And finally, if we have SO4 2 minus, all we need to do is add the hydrogen. Right? Remember, sulfuric acid contains of two parts. It contains of the hydrogens, because obviously it's acid, and then also the sulfate part, right? So if I have hydrogens as well, how many hydrogens do I need to balance out this charge? SO4 2 minus, I would need obviously two hydrogens. I would need two hydrogens, right? So I would need H2 here. So because again, each hydrogen contains a 1 plus charge, right? So if I have two hydrogens here, I can these will bond with the sulfate ion to get H2SO4 here. So this is H2SO4, and this would be our chemical formula for sulfuric acid, H2SO4, like so. And as you can see, this is the correct answer, H2SO4. If H2S is also a common answer that a lot of people find here. So if you wrote H2S, this here is actually the incorrect answer. So H2S, let me write down H2S for you here. My pen works. There you go. H2S is actually a hydrogen sulfide. Hydrogen sulfide. You have to really look at the prefixes here. IDE and ATE here are very, very different. IDE just refers to the sulfur atom. ATE refers to the polyatomic sulfate. So you have to make sure that we know which ones we're talking about. In this case, we're talking about the polyatomic here, sulfate. Remember, ic becomes ate, not ide here. So this here, hydrogen sulfide here would be an incorrect answer if you were to use this as well. So this here is correct. So that's number 1. H2SO4 is our answer here. So here's correct. So good solution. Great analysis here. Let's look at this question here. Number 2 is asking us, how do you find the molar mass of argon? I'm going to have to bring up a periodic table here. So periodic table here. So it's asking us, how do you find the molar mass of argon? I want to find the molar mass of argon. So again, very, very classic question in grade 11 chemistry. They are going to ask you to change between moles, molar mass, and obviously mass here. And we know that molar mass here is our big M. Right? We know this relationship is moles equals mass over molar mass, right? And we know that through our grade 11 stoichiometry. So we really care about this guy here. This is the big M here is the molar mass, and it's measured in grams per mole here. So if we know it's measured in grams per mole, what we can do is the molar mass here, we can always find this from our periodic table, because we know that every element on the periodic table has a specific atomic mass, and this here, when we're calculating for moles here, this will also be our molar mass here. So we just simply have to look at where argon is on the periodic table. In this case, it is the noble gases here, and argon is number 18 here. So it's so number 18 here, I don't think you can see it, but it says 39.948 here. 39.948 here is our molar mass of argon. So I'm going to write down big M. So let me see, big M of argon is 39.9, I believe it's 948, yeah, 948 grams per mole. And this here is our molar mass for argon, and this here is our answer, right? So all we have to do is simply just look at our periodic table to find the molar mass, and that's always what we have to do when we look at our periodic table. In this case, argon, we know it's not a diatomic molecule, so argon exists by itself. So if it was a diatomic molecule, we would actually have to multiply by 2 because we have 2 atoms in the molecule. However, argon exists by itself; it's just Ar. So we only need to account for 1. So this here is the correct answer. 39.948 grams per mole is the correct answer for argon here. Yeah, so 39.948 grams per mole. The solution here is correct. Good analysis here. All right, so it's asking us now, This is an organic chemistry question, so we're looking at number 3 here. It's asking, provide the major organic product for each of the following transformations. So we basically have one guy here, and we have a cyclohexanone here. So we have a ketone group, and this here is now we're jumping into organic chemistry here, right? So this here is much again, we have kind of questions from all over the place here, but we have here we have a cyclohexanone here first. So let's look at let's go clockwise, and maybe for the sake of time, what we can do is we can actually just look at the answer and see and kind of reverse engineer the mechanism here, just so for the sake of time, so that we can kind of move on to the other questions, because there's technically 6 questions here in one question here. So the first question, or maybe I'll do one for you here. So the first one here is the first product here. If I'm looking on this left-hand side here, I'm going clockwise. I'm reacting cyclohexanone with lithium aluminum hydride, and I'm working it up with acid work up here. So we know that for a fact that lithium aluminum hydride here is it's oxidation. It's an oxidizing reagent. Sorry. That's what I'm trying to say. Oxidizing reagent here. So what we can do is we know that if it's an oxidation reaction here, what we can do is we're looking at the carbonyl group, and we're seeing that lithium aluminum hydride is a reducing agent, not oxidizing. I'm mixing up with potassium permanganate. Sorry. So as we know that LAH is a lithium aluminum hydride is a reducing agent. So what we can do with our first guy here, LAH, I'm just going to use LAH as my shorthand and acid work up here. We know it's going to be a reducing agent. So I'm going to reduce this ketone back into a alcohol, right? We can reduce this to an alcohol here. So we know that for a fact that number 1 here is a cyclohexane, and then it's actually a cyclohexanol, right? We're reducing this carbonyl group back into an alcohol. So this is our answer for number 3 here. And as you can see, they got it here as well. They reduced the ketone into an alcohol here. So number 1 here is correct. Let me look at number 2 here. So it's reacting with some sort of benzene group, benzene amine group, here, and then again with a little acid workup. And this here is going to make this here would be kind of a nucleophilic substitution, right? So you have again the benzene group, or not the benzene group, sorry, the ketone group like so. We're reacting with this benzene with NH2. And then an acid workup. So you can think of this as, again, you can think of these guys here as partial negative. This here is partial positive. And then this here would be, again, these lone pairs are partial negative. It's going to be attracted to this carbonyl. It's going to bump this guy out here. So you get some sort of intermediate, like so. You would get, and this would have a negative charge here. Yeah, and here you get the benzene group like so. You get some sort of negative charge. Oh, this is not partial negative. Sorry, this is actually contains a negative charge here. And then what it's going to do again, the H plus it's going to create some, it's going to protonate basically OH2 here. So you would get something like this, or protonate this O minus, sorry, not OH2, and it's going to become OH2 minus here. So I'm just kind of skipping steps here, but this is OH2 minus. This will have a positive charge now here, and the lone pairs from the hydrogen will collapse here, and then kick out this OH group to form our final product here, which is the cyclohexane group bonded with the nitrogen, or double bonded with the nitrogen, sorry, and then bonded to the benzene group here. So this here is our correct answer. Number 2 here is correct. So this is great also. Number 3 here is kind of the same mechanism as our benzene group here. Basically, again, another nucleophilic substitution. This N group here is going to attack the positively charged dipole carbon here, and then it's going to shift up, right? So again, you would have the same kind of intermediate like so with the O minus, and then it's going to again protonate using acid workup using the acid to get OH2, and then N here is going to simply kick out this OH2 and eliminate it by creating a double bond here. So this solution is also correct. Very, very similar to the mechanism for number 2. Number 3 here we have this is a phosphorus kind of we have a phosphorus ion and also a phosphorus cation, and we have this is a methyl anion complex. What it's going to do, indeed, it's going to reduce this O minus into an alkene. So it's actually a very, very strong reducing agent, and it can actually reduce it all the way back to an alkene because of this because of this kind of negatively charged methyl group is very, very, very strong as and it's just being stabilized by this positive phosphorus group. So again, this solution here is also correct. We have diol here. If we react it with a diol and also with acid here, again, exact same thing is going to happen. The negatively charged oxygen here is going to attack the positively charged carbon here, and then this guy here will make an it'll make a cyclic group as well, because we have the O minus is going to attack this side, and then the other O minuses can also attack this side as well. So you would have you would create a cyclic group using a diol here, and then finally what we have here is, I don't think they drew it well here, so let me redraw this one for you. But you're going to react it with basically cyanide. So you have a ketone here. I'm reacting with HCN. What you're going to get here is you're going to, again, we know that this here is positively charged. So this is negative. This here is positive, and you know that again, this nitrogen here is very negative, right? This here, the lone pairs here, going to attack this guy, bump this up. So you're going to get something like this. You're going to simple SN2 reaction here, and this will be CN here. So this here is going to be our product for the last question here. So this is just simply SN2 substitution, and you're going to get a CN group, a cyanide group on your cyclohexane. So this solution here is correct. They don't really have analysis, but I'm just saying it's the correct solution. They didn't really draw out the mechanisms like I did, but totally fine as well. Okay, so that's question, I believe that was question 3. Yeah, that was a very long question. Question 4 is asking, which combination is the best choice to prepare a buffer with a pH of 9? And we have ammonia and ammonium chloride. We have CH5, CH3N, and CH3, CH5NHCl. We have nitric acid and sodium nitrite. Or sorry, we have nitrous acid. Sorry, that's not nitric acid. It's nitrous acid and sodium nitrite. And we also have HCHO2 and NaCHO2, its conjugate base. So let me just list out these guys here. So we have number 4 here. So we want a buffer with pH equals 9. And then we have here, A here would give us NH3, NH4Cl. And then we have the Kb value here. The K, or the pKb value here is for NH3 is 4.75. B here I have C5H3N and also C3H5NHCl. We know that the pKb for C5H3N here equals 8.76. C here we have nitric acid, so HNO2, and we have sodium nitrite. And we know that the pK, I believe this is the pKa here, because we're talking about the acid here, the nitrous acid here of, this is HNO3. Here is 3.33. And then finally, scroll down here, we have our last guy here, which is HCHO2 and NaCHO2, and then the pKa for HCHO2 is I think it's just HCHO actually. I don't think there's a 2 here. Equals 3.74. I'm trying to draw that into my mind here, and I don't think there's a 2 here at all. Same with this one. I think it's just NaCHO, I believe. Let me just check. Yeah, I think it's because oxygen is double bonded to the carbon here. So I believe that's our solution here. Yeah, I'll make a double bond here. Okay, sweet. So we're given all 4 of these guys here, and we're making our buffer here. Right? We're talking about our buffer, and we want it to be in the range of pH 9, right? So in order for us to do that, how do we make a buffer? Well, our buffer works best here when it's at its half equivalence point, right? When pH equals half of pKa at its half equivalence point, then we know that this here would be our a great buffer here, right? Because our buffer here, it only tolerates a pH change of plus or minus 1, right? So buffer only works when our pH, it's going to resist change when it's plus or minus 1 here, right? So we care about that. And we also know that pH here equals pKa at half equivalence point. So at half EQ point here. So we know that it has to. So these 2 conditions have to be met here in order for us to get a buffer, or to have a buffer of pH 9 here. And we care about this pH 9 here because pH 9 here basically has to equal very, very close to our pKa value as well. So basically what I would do to these questions, I would convert all of these guys here into pKa. So and I want pH equals pKa. So you can assume that if I want a buffer of pH 9, my pKa also has to equal 9 here. So immediately I can take off C and D here, because my pKa here is obviously 3 and 3.74. So these 2 are not correct answers, not even close to 9 here. And then for these guys here, I would need to convert KB into Ka, right? So I know here that 14, or pKw here, pKw equals pKa plus pKb, and that has to equal 14, right? So in this case here, I know that pKa has to equal 14 minus 4.75. This here will give me a value of 14 minus 4.75 would give me a value of, this is 9.25 here. And then for this one here, it's 14 minus 8.76 here, which would give me a value of 8.76, give me a value of 5.24 here. It's 5.24. So this here would be our pKa of both our buffers here, right? So this here is the pKa. So as you can see, which one's closest to 9? A is closest to 9, right? So again, 9.25 is very, very close to 9 here. So the buffer that will be made here will be the ammonia and ammonium chloride would be best. 5.24 is no way close to 9 as well. So number 8, so A here is correct, because again, you need to know the relationship between pH and pKa, and you have to know that the pH has a tolerance of plus or minus 1 pH, right? Remember, pH here is it goes by a logarithmic scale, so the ratio is from 0.10 all the way up to 10, like so here. The ratio of concentration of conjugate base to the acid must be approximately in the range of 0.10 to 10, or you can say from the pH between plus or minus 1 here, and the buffer can act effectively on each side here. So we care about that here, and it says a buffer works best if concentration of acid and base is equal. So concentration of acid and the base here have to be equal, so in order for us to get a good buffer here. So they've calculated probably the pKa of those guys here, and they realize that pH equals pKa at half equivalence point. So we know that the pKa of A here is 9.25, which means it's going to make our best buffer here. So the solution, again, they said therefore option A is correct. So solution is correct, but I think they're missing. But no analysis really shown for the calculations of pKa values for all 4 options here. So I'm gonna say solution here is correct. All right, so this here would be number 5. So number 5, another organic chemistry question here. It says draw the major reaction draw the major organic product for the below reaction here. So we have a benzene, plus we have some sort of a cyclopentane with kind of a methyl group here. And then I'm going to react it with H2SO4, and then I'm going to get something here. So it says draw the major product for this reaction. So this student here wrote something that's completely off. I have 1, 2, 3, 4, 5, 6, 7, 8 kind of carbons here, when I have definitely more than 8 carbons. I have 6 here, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 plus 6 here, which is 12 carbons. So there's no way that this here is the correct answer. Again, I don't know why they have a Cl here. There's no chlorine here. I don't know where they're pulling this from. So solution is definitely incorrect here. It's not an SO2 reaction here. So how will we solve for this question, though? I have an acid here, and then I have a alkene here as well. So you can say that this guy here is acid, right? So you can say it's also H+. I have an alkene group here, and then finally I have a benzene group. So acid's not going to really react with the benzene group here. The benzene here is pretty stable by itself. But what we want to do is, for this question, is that I have the methyl group kind of give this problem away, in the sense that this acid here is going to depronate one of these hydrogens here. So that's the first step here. So if I have a or not, sorry, not depronate. It's going to pronate one of these guys here. So this hydrogen is going to be attracted to it's going to basically pronate one of these guys here to make to create a reaction here. So what I would do, let's think about this problem here, because hydrogen isn't going to pronate this immediately, so it's probably going to do something called we're going to basically create a resonance structure here. So basically I'm going to pronate this guy first. So I don't really care about the benzene here. I care about more so the cyclopentane group. I'm going to have, let's say that this is now pronated. So this is now a CH4 here. I still have my double bond. What it's going to do is I'm going to move this positive here. This is currently a primary carbocation. And what it's going to do is going to then shift. I'm going to bring this down to bring it down to get something like this here. I would get probably something like this. It's going to basically shift. I basically do. I'm drawing a resonance structure to see that this here will now create my double bond here, moving my double bond up, and then my carbocation, my primary cation, is now in the secondary position, right? So this here is much more stable than this first one here. So you can say it could belong to this carbon here or this carbon here, but this here is much more stable than the primary carbocation that was made here. So if assuming that this is actually being pronated and I get something like this, then I can add it. I can add my benzene group now here. And benzene here is going to obviously be attracted to this positive charge here, and I would get something like this. So my benzene group would be basically right attached to this carbon here. So I would get something like this here would get, I would basically get a carbon-carbon bond. So this here would be like so. yeah, this here would be our solution here. And I don't think we can do anything else to this problem here. But this here would be our major kind of product here, because we shifted our carbocation to the secondary position rather than the primary. The minor product would have been if I were to react the benzene with the primary carbocation here. So I believe this is the solution for this question. I'm not like 100% confident in this answer, just because acid here doesn't usually pronate something as well. It might pronate this the allylic group here, but I don't, because normally benzene is pretty unreactive here, unless I'm missing something. I don't think it's a Friedel-Crafts acylation. It doesn't have a Cl here, nor I don't think it's a Diels-Alder as well, because I would need heat here as well to get some kind of reaction here. So I'm thinking it's a pronation reaction, and then creating resonance structure to provide this most stable carbocation, and simply just a substitution here. So I'm pretty sure that this here is correct answer. This definitely is not the correct answer, so I'm going to say solution here is incorrect. Incorrect. I'm thinking that this is a protonation of methyl group, and then drawing resonance structure to create a more stabilized carbocation, and then a substitution reaction to link the benzene with the cyclopentane group. The solution here is incorrect. All right, that's number 5. Number 6 is asking us, rank the following elements by electron affinity from the most positive to the most negative EA value. So this is number 6, right? Yeah. Number 6 says, I care about rank by electron affinity, and from most positive to most negative value here. So when we talk about positive, this is my shorthand for positive, and this is my shorthand for negative. Positive means that energy is being absorbed, right? So energy is absorbed. You can think of it as a endothermic reaction. Negative values is energy is released, obviously. Is released, and you can think of this as an exothermic reaction here. And I want to rank these guys here. So I have Br bromine here. It's just in blue, actually. Did it freeze on me? No, there we go. So I have bromine here. I have sodium, so Na. Tellurium is Te, I believe. Te is this guy here. Helium is He. And finally, phosphorus is P, right? So let's look at this topic of electron affinity first. What is electron affinity? So what does EA stand for? Well, electron affinity here, as the solution says here, is the amount of energy released when an electron is added to a neutral atom, right? So I'm basically measuring the amount of energy when an electron is being added to the atom here. So I can say here, measure of energy when electron is added to element here. So let's talk about bromine first. So bromine here is our halogen group here. Very, very, very electronegative first. So it actually likes electrons. So if I add an electron into my bromine group, it's going to like it, right? Br has 7 valence electrons here. If I add a bromine here, it's going to be great because I want it to. It's going to release a lot of energies here. So bromine here will probably be the most negative here, and bromine here, as you can see here, bromine here likes this likes the electron that's being accepted. So again, I'm going to have a positive. It's going to energy will be absorbed, right? Energy will be absorbed here. Same with sodium. So sodium here, however, sodium again, if I add an electron to sodium here, it doesn't really make a difference. Sodium doesn't really make a difference because I have one valence electron. If I add another one here, it doesn't really release a lot of energy, just because again, it's still it's going to have a charge of 2 plus. It doesn't really do anything here. So let me just write down the I can write down some of the sample equations for you. So I'm going to basically write Br here plus 1 electron is going to give me Br minus. Same with Na here, plus 1 electron is going to give me Na. Na. If I add an electron here, it's going to I'm going to get Na minus. Yes, Na minus, and then so on and so forth here. So again, so sodium again doesn't really react much here with the electron that's being placed here. Tellurium, for example, here, because it's so far down in terms of the periodic table here, if I put a electron into to tellurium here, it will energy will be absorbed here, right? So again, I know that because if I'm looking at the column here, electron affinity increases in periods from left to right and decreases from top to bottom. So it's going to decrease as it goes from top to bottom here. So tellurium is pretty down in the it exists pretty yeah, it's not that, it's pretty far from the top of the periodic table. So this here would mean that I don't have a lot of electron affinity here. Same with bromine as well here. So again, the energy that's being released is not that much. So tellurium and bromine are correct here in terms of the order here, because they're very much like electrons here. But once they like electrons here, their only energy will be absorbed here. It doesn't really matter if I add an electron, because I don't get a lot of energy that's being released here. So tellurium and bromine are correct. Sodium is next here because if sodium doesn't want an electron. It wants the electron to be taken away, right? So if I add an electron to sodium here, it's going to release some type of energy. Same with this phosphorus here. Phosphorus here exists pretty high up on the periodic table here, and again, this has 5 valence electrons. If I add another one here, it's going to release some type of energy, right? And if I want phosphorus to become a neutral atom here, I would need 3 more electrons. And this is only giving it 1, so therefore it will release some type of energy as so. And then finally, helium is going to have the most negative electron affinity here, because it's helium has 2 valence electrons. It's already happy, right? If I make a anion that is helium, or helium anion, is going to release a lot of energy here, because helium doesn't want another electron here. It's already stable as itself. So even if I decrease the amount of electrons or increase the amount of electrons here, it's going to make it very, very, very reactive here. So this solution here is correct. Good analysis here. All this is flipped, kind of. So let me redraw this question for you, so you're not bending your neck here. I have to bend my neck. So let's see, 7 here. It says aspartic acid at pH 1, pH 7 include hydrogen atoms. So this is actually a biochemistry question. So I'm not actually that familiar with biochemistry, but I will do my best to try to figure this out here. So H3N bond CH bond CH2 bond C. This is OH here. This is double bond O, my carboxylic acid group. Bond C, double bond O, bond OH. So this here is our aspartic acid, and this here is at pH 1. We want to draw it at pH 7 and pH 13 here. So basically what I'm going to do here is if I'm increasing the pH here, it's going to basically deprotonate our hydrogen atoms here, right? So which is the first hydrogen to be deprotonated as? So, well, I have here H3N positive here. So first it's going to deprotonate, obviously, this N group here. It's going to make it NH2+, because it's going to be now a neutral atom, right? So as you can see here, pH 7 Oh, so they actually depronate the carboxylic acid group here first. So the H's here are going to go away, going to basically depronate at pH 7. So let me draw that for you. And then at 13, it's going to depronate H3N here. So it really depends. I basically would need a chart for aspartic acids in order for me to solve this question, to see where the pKa's are, and to see the structures here. So again, very much a biochemistry question here that I'm not as familiar with. So I'm sorry about that. But I have this is pH 7 here, and as you can see, pH 7 means that I'm going to depronate my my hydrogens off the hydrogens that exist on my hydroxyl groups here. So let me just redraw this guy here, and I might run out of space here. So let me shift this up. So here is double bond O, and this here. So they would basically depronate this guy here first. So this becomes O, and this becomes the negative charge here. Right? This is an O minus now. And then it will also depronate this guy here. Right? This guy here would be O minus as well. And that's exactly what I drew out here. Right? Again, it's being deprotonated here. And then finally, I would get my last depronation at pH 13 would depronate this guy here. So again, this here, what it should have wrote a positive charge here, but I did not. And this here would depronate. I would get H2 instead, and the charge will go away, right? So this here would be pH 13 here. So H2N here, and this would be my structure at pH 13. So this solution is correct. I believe the carboxylic acid hydrogens go depronate first, and then the amine one second. So this is my fault. It probably has to do with the pKa of ammonium and of NH3 here, and how this is more stable bond. It requires a higher base here for me to depronate these atoms here. So this group here. So this solution here is correct. So remember, if I'm increasing pH, is increasing the basicity, or is increasing or lowering the pH, or raising the pH here. It's going to basically depronate my my aspartic acid. If I increase the pH, obviously it's going to protonate I have abundance of H+, so it's going to protonate our aspartic acid here. So solution here is correct. No analysis provided, but I believe that so hydrogens on the alcohol group in the carboxylic acid functional group are deprotonated first before the amine group is deprotonated. Protonated. pH 13, and this one would be pH 7. So solution here is correct. This here, number 7. Number 8 is asking us now, provide the reagents necessary to carry the following conversion. So I can't really actually see this question here. This question is a lot harder to see. I believe it's number 8 or number 9 here. Yeah, number 8 here. Let me see if I can draw this out. So it says I'm going from a benzene group. So this is a 5-part question here. So I might actually have to I might just look at the solution again for the sake of time, and just to work this out, because again, this is 5 questions here. But let me see if I can draw out the first one for you as well. This is my benzene group, and I want it to become a benzene group with a isopropyl on carbon 1, and then a propyl group here. So this here is good. They're using a Friedel-Crafts acylation to get my isopropyl group here, and then another Friedel-Crafts alkylation to get the first group, and the acylation to get my second group. I don't know if it actually bonds para to the benzene, so I might have to. I'm gonna look at the solution here, and as you can see, it's all benzene. Oh, so these are all reactions with benzene. So this is actually pretty good. So what they're doing here is, again, I have, they forgot this Cl group here, because again, this is a Friedelskraft acylation group. I'll bond, so this will go isopropyl. So again, I have a kind of an isopropyl group here, or chloroisopropyl here, and I reacted with AlCl3, so a very, very common Friedelskraft acylation reagent here, and then I'm going to get this first part here, which is great. And then finally, this is the first part is the Friedelskraft alkylation, and this here is the acylation, right? I have the double bond O carbonyl group with the Cl with NaCl with AlCl. It's going to bond para to the benzene here, and then finally I'm going to use a reduction reagent to which is this zinc mercury kind of reagent here. It's going to reduce this carbonyl group into back into just an alkane group. So this solution here is correct. The first one here is good, right? So again, basically when we're looking at these solutions here, I'm looking at how do I make the top part, how do I make the bottom part, and how do I get rid of the stuff on the bottom part here. So you can basically do something, you can basically use a retrosynthesis to think about this problem here. Again, when we're talking about the benzene groups, every time we have more carbons on the benzene group here, we're thinking of a Friedelskraft acylation or an alkylation, depending on how geometrically which one is more preferred here. So first solution here is correct. Second solution, I want a benzene, and this here is an ethyl group on 1 and a bromine group on 2. So again, we can again do a Friedelskraft alkylation to get my ethyl group into on carbon 1. So the solution here is correct. And then finally, what I'm gonna do here is, if I want to get my bromine group here, I have to do another step. I'm going to have to basically protect my benzene group, right? If I added Br2 FeBr3 into this first guy, so let me draw that out for you, because this here might get a little bit confusing. So if I were to, again, I'm doing my Friedelskraft acylation here, or sorry, alkylation. I don't know why I keep saying acylation. AlCl3 here. It's going to bond. This is a 3. This is going to bond to carbon 1, obviously. And that's no mistake about it. So this here is my ethyl group here. But if I were to react this with Br2 FeBr3, FeBr3 here, I'm actually going to get a bromine group that's para to the ethyl group here. It's going to bond to the opposite group, and why that is because it doesn't actually like being in the ortho position because of the ethyl group, because of steric hindrance here. It's going to bond obviously it's going to create the most space here. So if I were to bond the bromine here, it's not going to actually bond to carbon 2. It's going to bond at carbon 4 here, the para position here. So in order for us to bond, force it to go ortho here, we wanted to protect this group here. So they're using this blockage group here, this nitrate, this nitric acid. We're using nitric acid to create a protecting group on the in the para position. So you get NO2 here, and then you can do FeBr3 to bond it to the ortho position here. And finally, if I were to get rid of the protecting group, I'm using tin hydrochloric acid, sodium amide, and also H3PO2 is phosphorus acid. Phosphorus acid, yes, correct. In order for me to get rid of the NO2 here. So this solution here is again correct. Number 8 is C is asking us, I have benzene group, I want to make a carboxylic acid at the top and a chlorine group at the bottom. So exactly the same thing here. What I want to do is, again, I can Friedelskraft's alkylation to get toluene here, which is simply a methyl group bond to the benzene. And again, Cl2 here and FeCl3 here will bond in terms of the para position, which is good because I want something in the para position. I want Cl here. Again, I don't need my blocking group, protection group here because I don't want it to be in the ortho position. And then finally, I'm going to basically oxidize this all the way to a carboxylic acid using a very, very strong oxidation agent, so KMNO4, potassium permanganate, and with potassium hydroxide here. And it's going to get my carboxylic acid at the top here. And this solution will will be correct. What you could do as well with this synthesis chart here as well is you could actually do a Fritos craft first, and then, or actually you don't even need to do a Fritos craft. Oh, actually, no, you do need to do a Fritos craft first because I need to have a carbon here as well. So Fritos craft first, and then what we can do is uh, uh, we could create a halogen group as here as well, and then obviously do an SN2 to create alcohol and then oxidize it. But this here is the best solution here because I'm going from it's only taking 2 steps, right? I have it's creating a Cl group that's para to the methyl group here, and then finally I'm simply oxidizing my creating a very strong oxidization reagent to oxidize this methyl group here into a carboxylic acid. Number 4 here, D here, is asking us, I want a cyanide group that's kind of isopropyl to the on carbon 1, and then finally a SO3H here as well. So what I could do is I can again use a Fritos craft alkylation to get my to get an alpha group at the top here. I can use SO3, so again a sulfate group or sulfite group, sorry, and fuming sulfuric acid to get my protecting group SO3H. Again, this is a very good protecting group as well, and it's going to again it's going to form para to my the para position, obviously, and again you can use NBS here and ultraviolet light to get basically brominate my carbon 1 here, and then use either KCN or HCN to create the cyanide group here. So this solution here is also correct. Yeah, the solution is correct. I need to use MBS here to create a bromine on carbon 1 here. I don't think BR2 would not work in this. You can't use radical halogenation on an aromatic compound. You would basically need MBS, which is much more selective for the alpha carbon here. Finally, number E is a benzene group. I want bromine on carbon 1 and carbon 5 here, and then the isopropyl group. So again, if I want to form, I'm obviously forming the isopropyl group first. So I'm going to do a Fritos craft alkylation. Sorry, I keep mixing those up. It's an alkylation group. It's isopropyl on carbon 1, which is good. I want to now block my para group here. So I'm going to use again nitric acid and fuming sulfuric acid to block off the para group, so I can brominate. Again, excess bromination would give me a bromine is going to bond on this carbon and this carbon as well. And then finally, to get rid of the protected group, I have to use tin hydrochloric acid, sodium amide, and hydrochloric acid, and obviously phosphorus acid here. So these solutions are all correct. Again, this student, I believe they probably answered this question almost correctly. They failed to draw the isopropyl group here. That's okay. They blocked it off and they use excess. And they're just forgetting the reagents to take off the protecting group here. So they're the solution is very, very close to the solution provided, but this is a much more efficient way to solve for this problem here. So the solution is correct. Good analysis here. I like how they drew it kind of step by step here. That's number 8 here. Let's look at number 9. I only have a couple more minutes left for this problem, so maybe I'll do 2 more. So what is a quantum mechanical orbital? So again, this is a basically kind of grade 12 question. Quantum mechanical orbital just means that so we know that orbitals here is simply just empty space, right? It's empty space where electrons, or where possibility of electrons can reside in. So possibility of electrons can exist here, right? So when we're talking about the SBDF orbitals here, these are all orbitals, right? So these are all kind of shapes in which electrons can exist in. So these are all, it's basically, we're talking about kind of the Schrodinger model when we're talking about quantum mechanical model, right? So it's talking about how electrons exist in terms of, they can exist again in terms of waves, and we can use waves to help us explain the quantum mechanical model and how we're talking about the probability in where the electron can be found here. So it can be found in these orbitals. So when we do the math behind it, very, very advanced math, obviously that I can't even do, this math here is more so helping us find the probability in which the electrons exist, and it helps us create in terms of an orbital here graphically. So, or sorry, visually we see an orbital, and these are where electrons can be most likely found in terms of in space here, and in terms of that element here. So that's kind of what a quantum mechanical orbital is. It's simply just empty space where possibility of electrons can exist in, and this is determined by the Schrödinger equation. So it's helping us to determine whether the probability of electron can exist or may not exist in the orbital here. And you can think of this as, if you're talking, and if you want to go more in depth into the Schrödinger's equation, you can talk about the position versus the momentum of the electron, right? So as we hone into the position of the electron, we won't know the momentum of the electron as well, or the speed of the electron. Momentum, and you can convert that to speed, obviously. And then if we know how fast the electron is moving more precisely, then we know with more certainty whether the electron exists in that position as well. So I'm going to say here the solution is correct, but again, analysis is missing stuff, right? Like I don't like the grammar is not really there. Like the and orbitals are represented as, like, analysis is missing here. So I'm going to say solution is correct because the first part here is correct. I'm going to say orbitals are simply empty space where possibility of electrons can exist in. SPDF orbitals are energy, correspond to energy levels where electron can exist in. Quantum mechanical orbital just relates electrons to waves and helps us calculate the probability in which electrons can exist in the orbital. So solution here is correct. And then finally, I'm going to do the last question here, number 10. I had 11 questions, but I guess we'll end off with this question here. It's rank these elements in terms of first ionization energy to the lowest. So again, very easy grade 11 problem here. So I want highest ionization energy to lowest ionization energy. So if you recall, the ionization energy is simply the energy in which, if I were to take away an electron from the element, the energy is being released, right? So for example, for boron here, if I take away one electron here, what I'm going to get B plus 1 E minus, and I'm going to input some energy here, right? So it's kind of the opposite of electron affinity here. So I'm going to boron plus some type of ionization energy is going to give me boron minus plus 1E, right? It's going to, boron plus and 1E minus here. So this here, again, I'm basically removing an electron, but I'm putting energy into the element here, and it's going to remove an electron, right? So as you can see, ionization energy, if I were to remove an electron here, I would get, if I'm looking at this guys here, I have boron, nitrogen, fluorine, lithium here, oxygen, beryllium, and neon. So they actually all exist in terms of this the second row here, and we can know that ionization energy is going to increase as I go from left to right, right? So because it's going to be a lot harder for me to take away an electron, so I know that IE here increases from left to right. And if they all exist in the left or right, then I can basically, and in highest to lowest here, I'm simply just going backwards. So I can say basically it's neon, and then it's fluorine, and then it's oxygen, and then it's nitrogen, and then it's carbon, and then boron, and beryllium, and lithium here. So that will be my solution as well. So this here is my correct, this here will be my solution. So this is, again, from highest to lowest here, I can simply write, so lithium here, so lithium will have the highest energy, obviously, and then it's actually boron next here, and we know that that's actually an exception to the row here, and that's because I might not have enough time to get into this, but boron here is a half-filled orbital here, and actually hybridizes to create a half-filled orbital. So boron actually has a lower ionization energy, so it's one of the exceptions. Then it's beryllium, and then it's carbon, and then it'll just follow simply the cycle here. So carbon, and then nitrogen, and then oxygen, fluorine, and then finally neon here. So this here will be my full order here. So solution here is incomplete because they didn't really rank these guys otherwise. So I'm going to say solution here is incomplete. I forgot to rank other elements. So I'm gonna write the solution here: boron, beryllium, carbon, nitrogen, oxygen, fluorine, and finally neon here. And boron is higher in ionization energy because boron hybridizes to create a half-filled orbital, therefore more stable, and it will take more energy for more energy to take away an electron from boron. So that's the only exception to this rule here. So the solution, I'm going to say, is incorrect because they didn't complete the solution here. So other than that, that's going to be it for my my kind of stream here. I'm going to start with this question back at 2 p.m. and we will work through the solutions here. And thank you so much for watching. You can tune in an hour. I'm going to do basically the exact same thing in terms of these chemistry problems here, and we will kind of work together with those problems. Again, thank you so much for watching. If you like the stuff we're doing here, again, check out the YouTube channel at OneClass.com, youtube.com/OneClass, and you can check us out there. And yeah, thank you so much for watching. Again, remember to stay healthy, stay safe, and have a great day. Take care.